Swayam Prabha. Digital India. Educated India.
So, welcome all to this advanced calculus for engineers, and there are 4 modules in this course. Number 1 will be talking on differential calculus, the other module will be on differential equations, followed by integral calculus, and then at the end we will go through the vector calculus. So, this is lecture number 1 on very fundamental theorems, the so called Rowe's theorem. So, here in this mean value theorem, we will go through the statement of the Rowe's theorem, followed by the proof of this theorem, which is a very fundamental theorem of differential calculus, and then there will be some applications or worked problems. We will see the applications of the Rowe's theorem for solving several problems related to defining the roots of polynomial equations, inequalities, and so on. So, these 5 lectures, this is one of them, will be on single variable calculus, and then in the next week we will move to multivariable calculus. So, here coming to the proof of this Rowe's theorem, or first the statement, then we will see the proof. If a function f, so we are defining some conditions on the function f. So, if a function f is continuous in closed interval a and b, so the function has to be continuous in the closed interval a b and differentiable in the open interval a b. So, that is the another condition we are talking about on the function. So, the continuity in the closed interval and differentiability in the open interval, and the third condition is that the value of this function at a and b, it should be equal. So, what is the meaning here of all these 3 conditions? That we will just check one by one. But if these conditions are met, if these 3 conditions are met, then there exists a number c in the open interval a b such that the derivative of the function at this point c is equal to 0, or the tangent at this point c will be parallel to the x axis. This is the meaning here. So, this theorem says if these 3 conditions are met, what are these 3 conditions? The continuity of the function in the closed interval, then differentiability of the function in the open interval, and then the function value at a and b both are equal, then there exists at least one number. So, there might be more than one such point in this open interval, but this theorem says that there will exist definitely one number or at least one number such that f prime c. So, the derivative will vanish of this function at that point. So, what is the geometrical meaning of this? So, suppose we have a function where here the function value at a and also at b here. So, this is f b at the point b, and the value of the function here is f a. So, this f a is equal to f b at this point, and then the function is also continuous, as we can see in the graph. Also the function is smooth. So, it is very it is differentiable at all points in the open interval a b. So, all the conditions of this Rowe's theorem are met for this particular function. For instance, then the conclusion of the Roche theorem is that there will exist a number C. So, at least one number C where the derivative will vanish. So, in this case you can observe these numbers are many. So, for instance, here the derivative of the function is 0. At this point also we will see the derivative of the function is 0. At this point as well we will observe that this tangent is parallel to the x axis, meaning this derivative at this point is 0. So, in this case we can see that there are indeed 3 points where the derivative of the function vanishes or the tangent is parallel to the x axis. So, this is again represented here in the plot. So, at these 3 points you can see that these tangent are parallel to x axis. Coming back to the proof of this Roche theorem, we suppose here that big M and small m are the maximum and minimum of f in the closed interval a b. So, big M means the maximum and small m meaning the minimum. So, we assume that big M is the maximum of the function f in the closed interval a b, and this small m is the minimum of the function f in this closed interval a b. And this extreme value theorem says, which is another result, which says that a continuous function in this closed interval reaches its maximum and minimum. So, if we are talking about the closed interval, which is the case here a to b, and our function is a continuous function, then this extreme value theorem says that definitely there will be a maximum and minimum. So, there is no question of existence of this maximum and minimum in this closed interval of this continuous function. So, definitely there will be a big M, there will be a small m in the interval a b, in the closed interval a b. So, case 1 we are considering when the big M is equal to small m. So, what is this case? If we are saying that the maximum value of the function in this closed interval a b is some m, and also the smallest value. So, the local minimum basically of this function in the closed interval is also equal to m. So, this can happen when the function is basically a constant function. So, if your function is a constant function, in that case you will observe that the big M is equal to small m, when this big M is the maximum of the function and small m is the minimum of the function. So, in this case the function is a constant function, and for the constant function you can see that at each and every point in the domain a b, you can take any point, the tangent at that point of this function will be parallel to x axis, or for a constant function the derivative is 0 everywhere. So, here you have infinitely many points basically where the conclusion of the Roche theorem holds. Well, so this case is trivial, where we see that there are many such points where the derivative is equal to 0. So, we will go to more interesting case where suppose this big M and small m are maximum and minimum of f as we have assumed before, and if we assume local minimum, local maximum, that is fine. So, basically this m is the local maximum and big M is the local minimum of f of this function a b. So, in this case we assume that this big M is not equal to small m, and the situation may be that this maximum value, the local maximum value here for instance is this one, which is different than this equal value of the function f a and f b. Or it may happen that there is a function of this nature where you have the minimum. So, small m is here, but this small m is also different than the equal value. So, the equal value of this function, so f a f b, f a or f b, it is also different than f a and f b. Or the situation may be that we have the maximum and minimum of the function there in this closed interval a b, and in that situation also both basically are different than f a and f b. So, having said this, the m is not equal to small m, and definitely either the maximum will be different than the value of the function at a and b, or the minimum will be different than the function value at a and b. So, suppose for simplicity we can assume the small m also. So, the minimum value also. Suppose this big M is different from the equal values f a and f b, and let this f c is equal to m. So, because this m big M is attained in the interval this a to b. So, we say that is the c, the value where the function attains its maximum, its local maximum m big M, that point is c, which belongs to this open interval a and b. So, if m is different from the equal values and we have considered that is the point c where f c is equal to m, in that case, since this f c is the maximum value, or at least the local maximum, it is the local maximum of the function. So, what we have, that f c plus delta x minus this f c. So, if we subtract from f c plus delta x this f c, then what will be the sign of this expression here? Because f c plus delta x, this is a point in the neighborhood of this c. So, the function value in the neighborhood of this point c will be less than the function value at c, because f c is the maximum value, it has the local maximum at the point c. So, f c plus delta x, this value will be smaller than f c value, because f c is the maximum, is the local maximum of the function. So, in that case, the sign of this expression f c plus delta x minus f c will be less than equal to 0 for delta x positive or delta x negative. Does not matter whether this delta x is positive or negative, because that defines just the neighborhood of this function at c. So, this f c plus delta x minus f c will be definitely less than or equal to 0 for delta x positive or negative. Well, having said this, if we divide this expression by delta x, then what will happen? Now, the sign will depend whether delta x is positive or delta x is negative, because this was less than 0, and now if we divide with positive delta x, the sign will remain as it is. So, it will be less than equal to 0 if this delta x is positive, and the sign will be greater than equal to 0 if this delta x is negative, because then we have here the negative number, here also we have this negative delta x, then this will become positive. So, this is in either case. So, if we go to the first case when delta x is positive and we let delta x approach to 0, in that case this quotient here f c plus delta x minus f c over delta x, this will become the derivative of the function. This will become the derivative of the function, because the function is differentiable. That is the assumption of the theorem, that function is differentiable. Then this limit, which is basically the right hand side limit for this, or the right derivative, but since the derivative exists, this will be equal to f prime c, and we have already the sign of this quotient for all values of delta x is negative. So, this is less than equal to 0, which is already coming from here. Now, in this case, when the delta x is negative, this quotient is greater than equal to 0, and now we are talking about here again the same limit. If we take the limit here as well for delta x negative, this will be again the derivative, it will be left derivative, but again the derivative exists, and this will be equal to f prime c, and which is from here, because for any value of delta x this is greater than equal to 0. So, the derivative here also will be greater than equal to 0. Now, we have two inequalities, one is the f prime c less than equal to 0, another one is f prime c greater than equal to 0, and if we mix the two, inequalities, because one says that f prime at c is less than equal to 0, another one say f prime c greater than equal to 0. So, both can be true when this f prime c is equal to 0, that is the only common point of these two. So, f prime c has to be 0. So, in this way we have proved basically that there is a point here. We have started with big M, which was the maximum value at this point, but we can do this analysis for the minimum point as well for considering the small m there, and similar steps again we will show that there is a point where the derivative becomes 0. Well, so there are few remarks where we need to be careful about the application of this Rowe's theorem. The one is that these hypotheses of the Rowe's theorem, so all these conditions, continuity, differentiability and these equal values are sufficient, but not necessary for the conclusion. What does it mean? If these conditions, what are these conditions? These conditions are the continuity of f in the closed interval, differentiability in the open interval, and the third condition was f a is equal to f b. So, if these conditions are met, then we have the conclusion that there will be a point C in the open interval a to b where the derivative will vanish. So, these are the sufficient condition, not necessary. What do we mean by that? So, if these conditions hold, definitely we have such a point where derivative vanish, but if one of these conditions do not or does not hold, so in that case the derivative may be 0, may not be 0. We cannot conclude anything, because these are not necessary conditions for such conclusions. They are sufficient, they are more than what actually need, because this conclusion can be there without fulfilling any of these conditions. But the Rowe's theorem says that if these conditions are met, then definitely we have such a point where the derivative will vanish. So, that one has to be very careful. So, if all three hypotheses are met, then conclusion is guaranteed. However, if the hypotheses are not met, for instance, then you may or may not reach to the conclusion. So, we will see some examples which support that these are sufficient conditions, not necessary. So, for instance, if we consider f x, x square in the range minus 2 to 1 and 3x minus 2 in the range 1 to 2. So, if we consider this function, what is happening we will see. So, let us plot this for clarity. So, we have here this is x square, the part of the parabola from minus 2 to 1 up to here, and then we have this straight line 3x minus 2. So, what we can observe that at this point, at the point here this 1, if we check the derivative whether it is differentiable or not, we will observe that the derivative of this the part of the curve which is line is basically 3, and if we approach to this point from the parabola, it will be 2. So, you have the two different derivatives from these two sides, definitely the derivative does not exist. So, for this function at this point it is not differentiable, whereas it is continuous, because at 1 this is also approaching to 1 here, and this also at 1 is approaching to 1. So, the function is continuous, but it is not differentiable at this point. That means, all these hypotheses of these Rowe's theorem are not met, because the function is not differentiable in this interval. All other conditions are met, the function values at a and b are same, function is continuous, but it is not differentiable in this open interval minus 2 to 2. But what do we see, that there is a point here where the tangent is parallel to the x axis, but this is not the conclusion of the, because of the Rowe's theorem. This conclusion is not because of the Rowe's theorem, but for this function there is a point where the tangent is parallel to the x axis, but this conclusion is not came from the Rowe's theorem. So, as it is written here that you may or may not reach the conclusion. So, in this case we are reaching the conclusion, but that is not because of the Roche theorem. Suppose you consider another example where we have x in the interval 0 to 1 and then we have 1 to 2, our value is 2 minus x. So, we have this situation here. So, again this function is not differentiable at one point, but all other conditions are met, the function is continuous, also the function value at a and b both are 0. So, f 0 is equal to f 2 is equal to 0, that condition is also met, continuity condition is met, but the function is not differentiable at one point. So, that is the only point where we are losing one of the conditions of this Roche theorem. And as a result, what we see in this case, in this particular case, we do not have any point from this a to b where the tangent is parallel to the x axis. So, in this particular case, this conclusion is not met basically, but in the other case, as we have seen in the previous example, here in this example also the function was just not differentiable at one point, but the conclusion was met. So, it has nothing to do with the Roche theorem. The Roche theorem says if all these conditions, the condition number A, condition number B, condition number C, so one was the continuity, then we had differentiability, then we have f a is equal to f b, all these conditions are met, then we have that conclusion. So, that is the sufficient condition, not necessary condition, that you may or may not have a conclusion if basically all the conditions are not, all the hypotheses are not met, which you have seen clearly in these two examples. Both the examples, continuity and the function value, those conditions are met, but one was, I mean both functions are not differentiable at one point in the domain, and as you can see in one of them you still have the function at one point where the derivative vanishes, and in the other case we do not have such a point. Well, remark 2 is the continuity condition for the function on the closed interval is essential. So, this continuity we have taken on the closed interval and differentiability in the open interval. So, this closed interval is very important because one can easily construct a function. For instance, here that function is x in the interval 0 to 1 and then x is equal to 1, we have defined it as 0. That means f is continuous and differentiable on the open interval. So, here the continuity is there in the open interval 0 to 1, there is no problem because we have this function x which is continuous in the interval 0 to 1, and also this f 0 is equal to f 1, that is also there. So, all conditions are met except the continuity at 0, the continuity at 1. So, only at one point, that to end point the continuity is not met, and as a result, as you can see, so this is the function and at this point it is not continuous, the function is not continuous, and because of this, because now we are not meeting all the hypotheses of the Roche theorem, and as a result we do not have the conclusion also in this case. So, all the conditions whatever is written, continuity in the closed interval, differentiability in the open interval, and then we have the function value f 0 is equal to f 1, all these three conditions are important, and once we have these three conditions, definitely there will be a point where the derivative will vanish. Okay. So, some more examples. So, here we discuss the applicability of the Roche theorem to the function this x cube plus 1 and 3 minus x. So, what is happening in this function? So, f 0 is 1 and f 2 is also f 0 is equal to f 2. So, that condition is there. Then regarding the continuity, so we need to check continuity at 1 because otherwise this is of course continuous in 0 1 and this is also continuous in 1 2. So, we will check the continuity at 1, and at 1 we have the continuity because this value will approach to 2 and this value at 1 will also approach to 2. So, we have the continuity of the function as well. Coming back to the differentiability condition, we have to again be careful checking continuity differentiability at 1 because at all other points there is no problem about differentiability. So, at 1 from this side if you see you will have the derivative 3 and from this side you have derivative 1. So, the function is not differentiable at this point, which you can visualize from the graph itself. So, you have this function here x cube plus 1 and then you have 3 minus x, and at this point the function is not differentiable. You have two different tangents along this curve, you have this tangent and then you have a different tangent there. So, the function is not differentiable at this point. Well, so we cannot of course apply there the Rowe's theorem. Now, coming to the next example, using Rowe's theorem, show that the equation x 11 plus 7 x 3 minus 2 equal to 0 has exactly one real root in 0 and 1. So, what we will show here using Rowe's theorem, of course, there could be other ways also to show that this function, this equation has exactly one real root in the interval 0 to 1, but here we will use Rowe's theorem and will show that this equation has exactly one real root in 0 1. How to show that? So, suppose, so this is by contradiction actually. So, we will suppose that it has more than one real root. Yeah. So, it has 2, 3, 4 roots. We have assumed that it has more than one real root in 0 to 1. So, you pick those just two roots. So, take any two roots, say alpha and beta. If we assume that it has more than one real root, we can definitely pick 2. So, alpha and beta. That means, at this alpha and beta we have f alpha is equal to 0 and f beta is equal to 0, because these are alpha and beta are the roots of this equation. So, they will make this to 0. So, f alpha is 0, f beta is 0 in this 0 to 1 interval. So, alpha beta both are greater than 0 and less than 1, because neither of 0 or nor 1 is the root there. So, this alpha beta, these are the two roots which we have assumed, and they belong to this 0 to 1, in between 0 and 1. So, what we do now, we apply the Rowe's theorem, because our function is continuous, it is differentiable in the interval 0 to 1. We do not have to check that, it is a polynomial equation, and this polynomial obviously fulfill all these continuity and differentiability condition. Also, we have f a is equal to f alpha is equal to f beta is equal to 0. So, the function value is also same, and the Rowe's theorem says that there will be at least one point. So, there will be a point C in this interval alpha to beta where f derivative will vanish. That is the conclusion of the Rowe's theorem, which we can definitely apply, because all the conditions are met, all the hypotheses are met, continuity, differentiability, and then we have the function values at these 2 points are equal. So, definitely we can apply the Rowe's theorem. And now, as a conclusion of the Rowe's theorem, that the derivative must vanish at this point. So, what is the derivative of this function? So, the derivative of this function is 11 c 10 at c plus 21 c square, that is all, and as per the conclusion this has to be 0. So, this value has to be 0 for some c, and c is greater than 0 and less than 1. So, as you can see here that c power 10 and c square for non-negative c or whatever c, basically this is not going to be 0, this is 0 when c is 0, but our c is somewhere between alpha and beta. So, c is definitely greater than 0. So, this cannot happen, this 11 c 10 plus 21 c square cannot be equal to 0 for any c in this interval. So, that means we have the contradiction, this expression cannot be 0, but if we assume that it has more than one real root, then we are coming to this conclusion which cannot happen. So, it is a contradiction. So, we get back to our assumption that we cannot have two real roots, 2 or more than 2 real roots for this function. Well, now it should have at least one root, that then only we can conclude that it has exactly one real root. So, we have excluded that it cannot have 2 or more than 2 real roots, but now we can easily see that f0 is minus 2 and f1 is 6. So, the function value here at 0 is minus 2 and f1 is 6, and the function is continuous. So, it will definitely pass through this x axis. So, that is the root basically. So, it confirms the existence of at least one root. So, one root is for sure there, which is coming from this intermediate value theorem, and what we observed that it cannot have more than one real root. So, therefore, it has exactly one real root in this interval 0 to 1. Okay. Well, so another example where we see that we have a function 0 to 4 twice differentiable in this interval 0 to 4, such that some values are defined here. f0 is -1, f1 is 2, f3 is -2, f4 is 4, and then we have this function gx d over dx of fx square. So, we need to find the minimum number of distinct root of the derivative of g. G is already the derivative of fx whole square, and then we are looking for the number of distinct roots of g prime, where we can confirm that there will be minimum that many distinct roots, maybe more, but minimum can we confirm for this g prime using the idea of the mean value theorem. Yes. So, here this is the behavior of the function f. So, f minus 1, then it is going to f1 as 2, and then again at 3 it is going to -2, and then again 4 it is going to the positive sign. So, what is happening here? We consider this g, which is the derivative. So, if we take the derivative, which is 2 f x f prime x. So, basically our function is f x into f prime x and multiply by 2. So, we will analyze this g function and in fact the minimum number of roots for the derivative of this function. So, first we check that at how many points this g will vanish, how many points this g will vanish, which we can easily observe from this function, because this function f is 0 at this point, then at this point, then at this point, and then here f prime x is also there, which we know that by the Rowe's theorem, because if the function has here the equal values, definitely there will be a point where the derivative will vanish. Here also these two equal values, function is continuous differentiable, there will be a point where the derivative will vanish. So, using Rowe's theorem we can see here easily that g is 0 at least 5 at 5 distinct point. What are these 5 distinct point? This is one point, this is another point, then you have third one, fourth one and fifth one. So, at these 3 points the function is 0, and at these 2 points the derivative is 0, and this is the product of the function and its derivative. So, the function g will vanish at all these 5 points, and now we are looking for the derivative where the derivative will vanish. Yeah. So, the roots of the derivative. So, where the derivative will vanish. So, by the application of the Rowe's theorem, it confirms the 4 derivatives again. Why 4 derivatives for g prime? So, here the function is 0, here this g. So, here the g is 0, here also the g is equal to 0 at this point. Then again Rowe's theorem if we apply, then there will be a point in between where g prime will be 0. Then we apply between these 2 points, again we will find that g prime is 0. We apply again at this and this point, then we will find again g prime is 0, and then at the end this point and this point we will apply, and then g prime is 0. So, 1, 2, 3, 4. So, there will be minimum 4 points where the Rowe's theorem will confirm that the g prime is 0. So, that is the minimum. This is the minimum number of points are 4. We have 4 distinct points for some function which fulfill this condition. We may have more than such 4 points, but minimum number of distinct roots for this g prime is 4, which is just confirmed using Rowe's theorem. Well, let us consider gx. We have d10 dx 10 and we have x square minus 1 power 10 find the number of distinct roots of g in R. Yeah, so number of distinct roots of g in R. We can easily do this using again mean value theorem. So, this g x is a polynomial of degree 10. First of all, we have to observe this because we are taking the derivative, the 10th derivative of x square minus 1 power 10. So, this is a polynomial first of all of degree 20, x power 20 will be the highest term and then the other terms will come. So, this is a polynomial of degree 20, and if we take again the 10th derivative of this, so we at the end we will get a polynomial of degree 10. So, this is a polynomial of degree 10 which confirms that g x can have at most 10 distinct real root, because the 10 degree polynomial we cannot have more than 10 distinct real root, that is the result we know. So, g x can have at most 10 distinct real roots, but whether they are distinct or not, that we have to see now using Rowe's theorem. So, using Rowe's theorem we can show that it has exactly 10 real roots. How to show that? We consider this f x, the function, this x square minus 1 power 10, that is equal to this x plus 1 power 10 and x minus 1 power 10, where easily we can see that this derivative also, whenever you take derivative, for example, the first derivative you take, so you will have 10 x plus 1 power 9, the second one as it is, and then you will have the first function as it is 10, and then from the second you will have x minus 1 power 9. So, you can see either in the all terms have x minus 1 and x plus 1. So, when you substitute plus 1 or minus 1, it will become 0, and this will continue for first order, second order up to ninth order, because when we go for the 10th order derivative, then it will not be 0, because there will be a term x plus 1 power 10 itself, and there will be x minus 1 power 10, and all other terms will have both the terms x plus 1, x minus 1, but these terms will not vanish. So, except the 10th order derivative, all other will vanish, whether the function itself, first order, second order, ninth order derivative. Now, why we are considering this, you can realize. So, f is 0 at plus 1 or minus 1, the function value of f is 0, and the derivative. So, by the Rowe's theorem we know that we have the function, the value at plus 1 minus 1 is equal, all continuity differentiability assumptions are met, then there will be point xi 1 where, or sometimes we call c 1 or xi 1 whatever. So, the derivative will vanish at this point, and xi 1 is between minus 1 to 1. So, this is a straight application of the Rowe's theorem. Then now what is the situation? We know already that f prime is also 0 at plus 1 and minus 1, and there is a point in between. So, we have now here plus minus 1, we have plus 1, and then in between somewhere we have this point xi 1. So, here also the derivative is equal to 0, here also the derivative is equal to 0, here also we have the derivative is equal to 0. Now, we apply in minus 1 to xi 1 Rowe's theorem again, there will be a point where the derivative of the derivative. So, f double prime will be 0. Same argument we can have here in the second interval, here also f double prime will be 0. So, there will be 2 points, at least 2 distinct point where the double derivative will vanish again by the application of the Rowe's theorem. So, there will be f double derivative of xi 2, f double derivative xi 3, where xi 2 is between minus 1 to xi 1 and xi 3 from xi 1 to 1. So, here the double derivative will vanish at 2 points, 2 distinct points. We continue this because we have this f up to 9th derivative plus minus 1, it is 0. So, we can continue that, and in the last step we will realize that we have the f 10th derivative has 10 distinct points, because with the same argument we continue, f double derivative has 2 distinct points, then triple derivative 3 distinct points, and so on. The 10th derivative will have, because when we reach to the 9th here, there will be 9 and plus 2 11, there will be 11 points where the 9th derivative will vanish, and then you continue with the 2 first, one derivative, again the derivative of the 9th order derivative, that means the 10th order derivative will vanish, and so on. So, in this way we confirm here that it has 10 distinct points, 10 distinct roots, exactly 10, because it has at most 10 distinct real roots, and we have seen here that all these 10 roots are distinct. Okay. Coming to the conclusion. So, here we have discussed basically that Rowe's theorem, a most fundamental theorem here of the differential calculus. So, if this function f is continuous in the closed interval, differentiable in the open interval, and we have that the function a is equal to function b, then what we have realized the conclusion is that there will be a number c in this a to b open interval where the derivative will vanish, as you can see here in this picture, that there will be a point c where the derivative will vanish. So, that is the Rowe's theorem. We will see more applications of the Rowe's theorem in the next lecture, and that will be again the extension of the Rowe's theorem for further to extend these mean value theorems. These are some references which are used to prepare this lecture, and I thank you very much for listening this lecture. Thank you.